I want to talk about linear functions and how we think about those linear functions in the context of real-world situations, and thinking about a better way to write linear functions than probably how you've been trained. Okay, so what are linear functions? Take a minute to think about this. I mean, here's a graph of a linear function, but like, what is happening here? You might think of a linear function as something that is mx plus b, like this. And I would like for you to think for a minute about like, what is the meaning of m and what is the meaning of b? I have this set up so that m and b are sliders, and I want you to see if you can predict what will happen, how will the graph change as I drag this m slider, and how will this graph change if I drag the b slider. Pause the video and think about that for a moment. You might even create your own graph with exactly this situation and test it out. Okay, so many people are going to say m is the slope, and that changes the tilt of the line. And b is the y-intercept, and that changes where the line crosses the y-axis. Now, this is all fine for talking about the characteristics of this graph of this function, but really we want to talk about like the meaning of the function itself. And for that, I want to talk about like the characteristics of what the function might be representing. So I want to be looking at math as modeling real world data. So I'm going to just put this away for a minute, and we're going to explore a couple of examples. So first one is going to be taxi fare. So in San Francisco, the taxi fare is calculated with a base rate of $3.50 plus 55 cents per fifth of a mile traveled. So let's think about how that would translate. I have a note here that says the fare is actually slightly more complicated than that, but we're using this simplified version. I'm going to put that note away. Okay, so how could we write a function for this? So the fare would be based on the number of miles. Let's call it d for distance. So it is calculated with a base rate of $3.50 plus 55 cents per fifth of a mile. So that looks like $3.50 plus 55 cents per fifth of a mile. So d over 5. Okay. So this is what that would look like. And let's call this f of d. And let's just double check that if I have f of 1, that's 1/5 of a mile. So that would add 11 cents to $3.50. So that'd be $3.61. Sounds good. Okay. Now, in this context, can we actually identify what is the slope and what is the y-intercept? If we look at slope and y-intercepts, the slope is the coefficient on the input variable, and the y-intercept is the constant. So in this case, we have the y-intercept is 350, and the slope is going to be the coefficient on the input variable. The input variable is d, and it's actually going to be 55 cents divided by 5. So, divided by 5, or 11 cents. Okay, now these are characteristics of the graph. And I want to talk about not characteristics of the graph, but like what do these numbers mean in the context of where we got this model from? So I want to talk about the characteristics of the function. Okay, so I'm going to take characteristics of the underlying function in context. So can I just, nope, I cannot. So what does this 3.5 mean? Oops. What is the context of that 350? And that is going to be really our starting value. And it's the starting output value. And I'm going to say when the input value d equals 0. Okay, it's the starting fare. Okay, and what about that 0.11? How can we phrase that as having meaning attached to that function? So that is the cost of the fare, or the addition to the fare per extra mile driven. And I could phrase this another way, that it's the rate of change. So that's really the mileage rate, right? So there's this base fare of $3.50, and then 11 cents is the mileage rate. So I'm going to say it's the rate of change of the output with respect to the input. Okay, so this is putting those two numbers, $3.50 and 11 cents, into the context of like, what does it mean in terms of how the function is operating, and not just characteristics of the graph. Okay, so I want to hold on to that. We have this sort of starting output value, which is, and let me actually put this in a slightly different light. The 350 in the taxi cab example this is going to be the base fare. Okay, so this is sort of looking at the $3.50 in context of the situation, but then also translating that to the meaning of where it stands in the function itself. Okay, so we're going to take this and take these concepts and kind of try to anchor back to these with a couple other examples. So here is a table of US tax brackets for the year tax year 2020. So there are 7 different tax brackets that are divided by income level. And each income level has a base tax dollar amount that you have to pay, plus a certain percentage that you have to pay for all of your income that is over that base amount. So for if your tax bracket, if your income is between $0 and $9,876 per year, then you have a base of $0, and you're basically charged, you're taxed 10% of your income. If your income is between $85,200 and $526 and $163,300, then you have this base tax amount. You have to pay $14,650.50 base rate, plus 24% of however much you earned over that $85,526. So let's see. There are 7 income brackets, and so there should be actually 7 functions that we should write. So let's look at this one piece at a time. There should be 7 different linear functions here. So let's do this. The first one, if I have an income level between 0 and $9,876, then my tax should be determined by a $0 starting amount plus 10% of my income. And my income is going to be X. All right. Let's actually show these. Okay. And it's worth kind of pointing out that, if I was to change my scale on this graph, I would see that this line is going to extend forever, and I only want it to extend for X up to this $9,876. So this should be, and in fact, X should be positive too. So I'm going to say 0 is less or equal to X, which is less than 9,876. All right. Let me change my, so this is income, and this is going to be tax in dollars. This is also in dollars. And looks like my income is going to be above 500,000. So let's say I'm going to go up to 600,000. And it's definitely going to be my taxes are going to be over $156,000 supposedly. So let's just guess $200,000. Okay. And there I am there's that tiniest little tax bracket for people who have an income less than 9,876. All right. So the second one, if I have a tax bracket that's between 9,876 and 40,126, then my base tax amount is $987.50. And then I have to pay 12% of all of my income that is above 9,876. So let me write that down. This is for income between okay. Okay, so that is what tax bracket 2 looks like. And if we build this into a model, this is going to be a base amount of $987.50 plus 12% of the income that goes over 9,876. So I'm going to say there's 12% of the amount that goes over that is x minus 9876. Okay. Again, what we see here is this is going to, for too large of a range, so I'm going to restrict the domain of this. This is for x between 9,876 and 40,126. So okay, so that is this piece here that we can see. Okay, so there we have income, the taxes for income bracket 2. All right, so you should take a minute to, you can do this yourself and create your little linear models. This is a really great exercise to create a linear model for each one of these tax brackets. And I am not going to do this, but let's just do one more of these. Let's do tax bracket 5. Okay, and I am going to copy this and paste it so that I just have the context of it here. Tax bracket 5. So tax bracket 5, here's 1, 2, 3, 4, 5. This is going to be between 163,301 and 207,351. The base rate is 33,271. So this is clearly outside of my tax bracket because I cannot imagine having a base of $33,000 that I would pay in taxes. Plus 32% of the amount that is over that. The amount that is over that lower range. Okay, so that's what tax bracket 5 looks like. Let's see if we can write this function. So we can start with setting our domain. This is for x between 163 301 and 207 351. By the way, Desmos does not like commas, and you'll see when it typesets it, it kind of puts a teeny tiny little space in those between the groups of 3 numbers where you might otherwise see a comma. But if I put a comma there, Desmos is like, I don't understand what's going on. Okay, so that's going to be my restricted domain. The base amount is going to be $33,271.50. And then 32% of the income that exceeds that $163,000. So it's going to be 32% of the amount that exceeds that. So it's x minus 163,301. All right. Okay, let's zoom out and see if that looks like it kind of, that looks like it could connect there in the middle. I am not going to fill in all the blanks. I think that it's a good exercise for you to do so. But I want to take a moment to look at the meaning of these numbers, okay? So what are these numbers? What are the meanings of these numbers? In the context of tax brackets, in the context of the behavior of the function. And in the context of the graph. So there's kind of three different ways to look at this function. One is in its real world meaning. One is in the thinking about the behavior of the function, how the function is changing. And then there's looking at the graph. And all three of these things are very much related. So let's look at that first number, 33,271.50. I'm going to put a comma in there because I'm just writing text here. So what is this in terms of the tax brackets? This is the base the base tax amount for that specific tax bracket. Okay. Now, what about in terms of the function? Okay, so we should be talking about the function in terms of input values and output values, and the how the function changes. So again, what does that mean in terms of the function? This is the starting output value. And what I mean by starting output value is where am I quote unquote starting in this instance? The place where I'm starting in this instance is when the input equals 163,301. Okay, so I kind of want to encode that number 163,301. So let's say this is for the tax bracket beginning with income 163,301. Okay, let's put the dollar signs in here. Okay, so this is the starting output value when the input is 163,301. And okay. And then, so that gives us meaning for two of the numbers in here. This is the 33,271 and the 163,301. So what about the meaning of that 0.32? Well, that is the income tax rate. Okay, and let's actually call this 32%. And so that gives us context for that 0.32. In terms of the function, this is now, what is that income tax rate? So that is the rate of increase of the function, of the output. Relative to increase in the input. Okay, so let's put this in context here. This is income tax rate for the current tax bracket. Yeah. Okay, that's fine. Okay, and it's so it's worth looking at this and seeing this all of these parts of this function. So this piece is our starting tax amount. It's the starting output value. This is my rate of increase. And this whole piece here is basically how much my income, that's the difference of where I am now versus that starting base income level. Okay, so it is worth kind of putting that in there too, that the X minus 163,301 is the amount that the input has changed since the starting amount, right? And let's put this in context of the numbers, and let's put that. So this is the amount of income over the base amount for the tax bracket. Okay. So looking back at the taxi example, what we had is, and we could have called this f of d equals 350 plus 0.11 d. Okay. And so our base fare was 350. That's the starting output where the input equals 0. And then this is the rate of change of the output with respect to the input. And the D is how far you've driven, which is basically how far you've gone in the starting function. And I want to actually put in, this is D minus 0. That is how far you've gone since your starting position, which was 0 miles. Okay, so we're doing really the same thing here. Okay, what we've got is our starting value, the rate of change of my output with respect to the input, and then how much my input has changed since my starting value. Okay, starting value with this particular input value. All right, and so we can actually see that point, 163,301 and 33,271.50. We can see that here on the graph. Okay. Many of you have actually learned the quote-unquote point slope form of a line. And I want you to relearn it. Okay. Many people see the point slope form of a linear equation is it's y minus y1 equals m times x minus x1, something like that. And if you look at what this means, like I hope that you are able to find some way to justify like how that is a point slope equation, but I want you to not just blindly use this. I want you to use this because it makes sense for linear equations. So instead of using that, so this is y as a function of x, or maybe I should not. Okay. And I'm going to write this as an equation. So we have y as a function of x is going to be, if I solve this equation for y, I can write that as y1 plus m times x minus x1. Okay? And what we see is our linear equation is we have some starting value y1 which is really the y value at x1. Okay, I'm going to call this f now, f of x. So we have some base starting value. We have some rate of change of the output value with respect to the input. And this is how far we have come since that input value, since we were at that input value. Okay, I want you to use this and internalize it and practice this as you are working through linear functions. Okay, so let me rewrite this as y. Okay. All right, and I actually want to get rid of this because there's other meanings of some of these variables later on. Okay. So I'll put this in quotes. And or that y1 is actually f of x1. Okay. So it's a good idea to practice actually writing all of these. There's basically 7 practice problems there. Okay. I'm going to leave this example and go to here, which is modeling some data. There is another video on modeling data. I'm going to just recap what we did for that here. So this data shows the carbon dioxide concentration in the atmosphere measured from a station on top of Mauna Loa. This goes from 1959 to 1969. I'm going to change my scale. The x-axis is going to be the year, and the y-axis is going to be CO2 concentration in parts per million. The x-axis is going to go from 1959 to 1969, and the y-axis is going to go from looks like 315 to 325. Okay. So zoom out a little bit. There's my data. All right. So we might be able to model this data, like what things do we observe are happening here? This looks roughly linear. And I want to actually use that 1959 as an anchor point here for our data. So if we were to use this model, if we were to model this with a linear function, one of the things we might say is the CO2 concentration, I'm just going to call it C, is going to be, it looks like the starting concentration is 315.97. That's the starting concentration in 1959. Plus, how much is it changing per year? It looks like from 1959 to 1960, it looks like it's changing by about 1%. Then it looks like a little less than 1%, a little less than 1%. So let's say it's changing at, I don't know, 0.9, and it's not percent, 1 part per million per year. And then, so it looks like, sorry, let's actually write this. In 1959, the CO2 concentration was 315.97, and it looks like the CO2 concentration went up a little less than 1 parts per million per year. Okay. So let's guess 0.9 parts per million per year. And so we have to figure out how many years we are after 1959. So that is x minus 1959. And so that is a line that actually goes through that point, that data point for 1959. And then it increases at 0.9 parts per million. I can make another stab at this, like maybe at 0.8. Okay. And yeah, I don't know what that number is. So, but this is something like I can play with this. Let's call this, I don't know, R for a rate of change. Nope. R looks like it's being used. I know that Q is not being used. So let's make a slider, and the slider should be between probably 0 and 1. And we can kind of slide it to figure out, that looks like a good fit. I kind of want to drop this a little bit. So in fact, I want to call this a different number. That's 315. Let's call this base. And let's go from 310 to 320. There we go. I don't know. That looks like maybe a good guess. And so this might be a good linear model that, and if we interpret what this means, that means that with a concentration level, a CO2 concentration level at 315.8 parts per million in the year 1959, it looks like the CO2 concentration is increasing at a rate of about 0.85 parts per million per year. So let me write that with a starting value of 315.8 parts per million in 1959. The CO2 concentration is increasing at a rate of about 0.85 parts per million per year. Okay. And of course, we can actually do a linear best fit for this. These data are called X1 and Y1. So I am going to I'm going to say my Y1 should equal some, letters, B1, nope, base 1, times plus some rate 1, times x minus 1959, and my x is x1, and I'm going to put a tilde here. Okay, now this tells me that my base level should be about 315.882. That is very close to what we found just by eyeballing it. But the rate of increase, they said, is, according to the best fit model, is about 0.80, which is less than what we had. So 0.80 is closer, and then, so this says this is a better fit than what we had. Close. But this is basically saying with a starting value of 315.882 parts per million in 1959, we increase our CO2 concentration at a rate of 0.80 parts per million per year. And this is like the number of years that we have gone past 1959. Okay. So there is another video that involves modeling linear functions, modeling different functions, modeling data. And you can see, like, if you were to zoom out on this and see what is the how the data continue past 1969, we can see that linear model, while it was a good fit from 1959 to 1969, it becomes a really, really terrible model. It starts curving up. And so there's another video on modeling this with exponential growth. Okay, just to recap, one of the things that we learned from this, when we have linear functions, what we want to do is we want to write them in this kind of point slope form, and it is related to the point slope form that you have learned in your pre-calculus classes. It is exactly the same form, basically just moving that y1 over to the right side, but I want to write it as, kind of concentrating on what is the output value. The output value is, we have this starting output value, y0, y0, when the input equals x0. So let's actually say y0 equals the starting output value when the input equals x0. And what is the r? R is going to be equal to the rate of change of the output per unit of increase of the input. And then it is important to notice that x minus x0 is how much the input has changed since the starting value. Okay, so take this as a way of kind of modeling your linear functions. This is going to be, like, as much as we are going to be dealing with very complex functions in calculus, one of the beautiful things that we are doing in calculus is boiling everything down to linear functions. And so you are going to be writing linear functions every single week this semester. So get accustomed to doing it in this way. It will make a lot more sense and help you move forward.